Good morning, class. This is note 6.9. I'd say it's 6.9, but it's actually probably a little bit earlier than 6.9, but that's fine. Because I go over the guided notes, this is a little bit extra information. Some of it's going to overlap from the guided notes, parts 1, 2, and I'm going to do a part 3 then. But let's take a quick look at this. This is the quantum mechanics part. So the scientist, the physicist, Erwin Schrödinger, developed a mathematical treatment for which both wave and particle nature of matter could be incorporated. I don't know if you know this or not, but Einstein at one point said there is an issue with the duality of particles where they acted like waves in one instance and they acted like particles, like point particles, in another instance. And one of Einstein's less famous discoveries of nature is he said, why can't it be both? So they called that the duality of the dual nature of matter that can be both the function of a wave and a point particle. As it turns out, electrons are exactly that particle. So if we're describing electrons outside the nucleus, then this is one of those situations where we have to account for both its wave properties and the particle nature of electrons. So when Schrödinger put these two concepts together, it's known as the quantum mechanics. Now, quantum mechanics are also almost always known for describing something when they call it the quantum world, they mean the very, very, very small world. So electrons fit into that very small world. So that's what quantum mechanics is, almost like a physics for the very small. And that's almost always how you hear it coined in terms of like being something very small. Okay, enough talking, me talking about quantum mechanics. Let's move on. So there is something called a wave equation. When a particle displays wave properties, then those properties can fit into a wave equation. You don't need to know the wave equation. The wave equation is typically given with this Greek letter psi, which is what you have here. The square of the wave equation gives a probability density of the map. Now this would be a probability density map of an S sublevel. Okay, and the reason why I can say it's the S sublevel is because if I take the 95% where the electron might be 95% of the time, it's spherical or it's ball-shaped. Okay, so that's what leads me to believe that this is a probability picture or a density map of the S sublevel. So this all does actually kind of fit together. So let's keep going here. As we keep going, so solving the wave equation gives a set of wave functions or orbitals. So the orbitals are what we want to talk about. So each orbital describes a spatial distribution of electron density. That just means each orbital describes a picture of where the electron could be. Okay, that's it. That's what this sentence means exactly. The orbital is described as a set of 3 quantum numbers. Now the quantum numbers, we already know them. We've already talked about them because they're already on the notes, the guided notes that we've talked about. I gave you 4 things, and 3 of them are quantum numbers describing where an orbital is. So the principal quantum number is also known as the main energy level. So this is nothing new. Okay? Describes the energy level on which the orbital resides. The value of n is in integers larger than 0. So 1, 2, 3, 4, theoretically it could go into infinity, but it goes up to 7 for us. The next one is the azimuthal quantum number. I didn't just make that name up, although it looks like I did. This is basically what we're talking about are sublevels. Okay, you know what sublevels are. They are the S, the P, the D, and the F. So those are the sublevels along with the shapes. They're values of n minus 1. So if n equals 2, then the sublevel or the azimuthal quantum numbers could be 0 and 1. Okay, so n minus 1, in this case, when I put 2 minus 1 equals a 1, and that's the highest it can be, and it can also be 0. So if I had an n equals 3, I could have an azimuthal quantum number, or an L, of 2, 1, and 0. Okay, that would be the S, the P, and the D. Okay, that's what those numbers mean. So when I subtract 1, that's the highest azimuthal quantum number you can have. And then they go in integers down to 0. Okay, so let's keep going. So the value of L, or the azimuthal quantum number, correlates to this. If it's a 0, it's an S. If it's a 1, it's a P, a 2, D, and a 3, and an F. And that's all we need for azimuthal quantum numbers. Now the magnetic quantum numbers are a little bit different. They describe the three-dimensional orientation of the orbital. We talked about orientations already in the guided notes. That's what orbitals are. They are orientations of the shape from the sublevels. So the values of are integers from negative L to positive L. So if you have n equals 1, the L equals 0, it must equal 0, and the m sub L also must equal 0 because there is no negative 0 to positive 0. That just doesn't happen. Think of a number line. Number line here has 0, there's a -1, there's a -2, there's a +1, and there's a +2, okay? That's a typical number line starting with 0 in the middle. And here we're going from +0 to -0, that means 0. If I'm going from like n equals 2, well then I can also have an L equal to 0, but I can also have an L equal to 1. And then that would be an m sub L of -1, 0, and +1, those three. Okay, so what is L with 1? L with 1 is P, and we know that P has 3 orbitals. Okay, and each orbital holds 2 electrons. That's why P can have a total of 6 electrons possible. So these orbitals are actually -1, 0, and +1. This is where the azimuthal quantum number and the sublevels, the magnetic quantum number and the orbitals are exactly the same thing. This is why P has 3 orbitals. Okay, keep going. So the magnetic quantum number, m sub L, orbitals with the same values of n for a shell. So take a look at this. So if we're talking about n, this is the main energy level down here at this thing here. So 1, 2, 3, and 4. The possible values of L are 0, but for n equals 2, it's 0 and 1. For n equals 3, it's 0, 1, 2. For n equals 4, it's 0, 1, 2, and 3. So these correlate exactly to the subshell designation, the things we use for electron configurations, as the 1s, the 2s, the 2p, the 3s, the 3p, the 3d, the 4s, the 4p, the 4d, and the 4f. Okay? Then the possible values of m sub L are obviously 0 anytime we have s's here, and then a -1, a 1, 0, -1 for p's, and then look, the d's have, where are the d's at? The d's are right here, and that's at 2, 1, 0, -1, -2. So D's have 5 orbitals, which of course we know they do, and the total number of orbitals in a shell means this, do you remember this? This is like total number of orbitals for a shell is just n squared, like that. If it were the number of electrons, because you can fit 2 electrons into each orbital, it would be 2n squared. But for just the number of orbitals in a shell, it's just n squared. Okay, so I'm going to keep moving here. I know I'm going to be talking for a little bit, and I apologize. So the s orbitals, we know what they look like. They look like spheres. You've seen this before. Here's something. If we have a 1s orbital, it looks like a sphere. If we have a 2s orbital, it looks like a sphere, but there's like a smaller sphere inside. So it's like we have the 1s is right here, but then slightly outside the 1s is a little place where the electron can be if we have an electron in the 2s, and then we have what's called a node. A node is where probability drops off to 0. And then so the places that you could have an electron distance from the nucleus would be a little spot there, and then the rest of it could be there. So the electron spends a very little bit of amount of time in there, but most of the time in there, because it's a much larger area. So the 1s is what you see very much in the center here, and then there's a little spot for the 2s, and then there's a node, that's the white part of my sphere, and then the rest of it there, the darker blue, would be the rest of the 2s. Now, if we have the 3s, there's actually 2 nodes, 2 places where the electron doesn't go. Okay, and that's what makes these s's look like that. Okay, so I'm going to continue on. So a node is just a place within the orbital where the electron just doesn't really go. So the p orbitals have a distribution on either side of the origin. Okay, so that's why this looks fuzzy. The first one looks fuzzy, but that would be a pz. Okay, here you have your pz, your px, and your py. And we draw them with like very certain edges, but they really don't have certain edges. They're very much a distribution, so they look fuzzy in actuality. These regions that we call orbitals, they all look fuzzy. So, but to give them a certain shape, though, we draw them with hard lines. Okay, the d orbital looks the same, except there's 4 that are clover-shaped and 1 that's not. A donut with around the center resembles a p orbital with a donut around the center. So, yeah, that's the d. You've seen these pictures already, so I'm going to keep going. Now, if we have hydrogen and there's only 1 electron, this is important. If we have hydrogen and there's only 1 electron, then that 1 electron can exist in the first main energy level, the second main energy level, the third main energy level, and notice that the s and the p are the same place, the same distance from the nucleus. Okay, the s, the p, and the d are all the same distance from the nucleus. So that means that the second main energy level has very tight constraints. In other words, like it doesn't range from a certain amount of distance from the nucleus to another. And there's no overlapping whatsoever. This is the important part. When we just have 1 electron, it's not repulsing anything. When we have more than 1 electron, then they start to repel each other, and then that starts to mess up the sublevels. Okay, here's what I mean. So first of all, let me use this vocab term. This is considered to be degenerate, which means that all of these sublevels stay at the same distance from so all of the second main energy level, the 2 sublevels are the same distance. Okay, that's degenerate. That means that they are the same energy-wise. And n equals 3, the s, the p, and the d all exist at the same distance from the nucleus. So it's degenerate. It is all happening at the same distance. Okay, but what happens when we have more than 1 electron? When we have more than 1 electron, they start to repel each other. Notice how the s and the p separate now. So the 2s and the 2p are separate. And then take a look at this. This is where things get a little crazy. The s, the p for the third main energy level are separate. Notice that the 4s dips down just a little bit below the 3d. Okay, this is why, well, I'll get into the, for the periodic table. But that's why potassium and calcium come first before the transition metals. But the transition metals, the first row of the transition metals, scandium and going across to zinc, they are all filling in the 3D. So the 3D is just 1 step above the 4S. So the 4S comes before the 3D. So this gives us like a very odd. Okay, so let's talk about the last part that has nothing to do with the orbitals, very little to do. There's a spin quantum number where we have 2 electrons. These electrons spin in opposite directions when they're in an orbital. They have to, otherwise they wouldn't be able to stay in the same, in the same place. So the spin is how we tell them apart when they're inside the same orbital. So the spin of an electron describes its magnetic field, which affects its energy. Okay, so let's keep going. This led to the 4th quantum number of m sub s. So the spin quantum number. The spin quantum number has only 2 allowed values, and that's a +1/2 and a -1/2. So that means when it's facing north, that's a +1/2, and when the spin allows it to face south, then it is -1/2. Okay, so we keep going. The Pauli exclusion principle says no 2 electrons can have exactly the same energy. That means that no 2 electrons can have exactly the same identical sets of quantum numbers. The quantum numbers describe the energy, so therefore, okay, let's keep going. Electron configurations. First number is the main energy level. The second is the P is the sublevel, which shows you what the shape of the orbital is. And the last one tells us the number of number of electrons in that sublevel. Okay? So the letter denoting the type of orbital, the subscript denoting the number of electrons in those orbitals. We've talked about this before. So orbital diagrams are exactly the same as electron configurations. The only difference is that now we are showing the actual electrons with half arrows pointing up and half arrows pointing down. When you put two electrons into the same orbital, they must be spinning in opposite directions. That's why you see the half arrows are facing in the opposite direction, and they must do that. To put an orbital to have like 1s like this and to have them doing the same thing simply cannot happen. One will flip to be the opposite. Okay, so Hund's rule says that electrons, notice the 2 here in 2p, there and there. They will split up because they repel each other. Remember that electrons repel. So if I have 3 orbitals in my 2p, but I only have 3 electrons, they will spread out first. Okay? That means that they stay as far apart from each other as possible. Remember that these orbitals are all at the same, they're degenerate, they're all at the same energy level. Okay, so that means that my px here is at the same energy as my pz. Okay, so that means that these electrons will spin positively, typically the same, but they will spread out first. That's Hund's rule. So the periodic table, I've shown you something like this before, where you have the 1s for hydrogen, that would be 1s1 for hydrogen, 1s2 for helium, and then you start to fill the 2s when you're in this block here, and then that jumps to 2p, and then you go 3s, and then 3p, and then 4s. Remember, the 4s dips down below the 3d, and then you fill the 3d, and then you do the 4p. This right here is how the electron, this is the electron configuration. 1s, 2s, 2p, yep, 3s, 3p, 4s, 3d, 4p, okay? Because these electrons repel each other, now there's enough of a separation between the main energy levels where here we have our first example of like the 4s dipping down below the end of the third main energy level. Okay, let's keep going. Some anomalies. Some irregularities occur when there are enough electrons to half-fill s and d orbitals on a given row. We'll talk about that later. I'll show you what's going on with that. So for instance, they'll say something like your configuration, instead of a 4s2, 3d4, you'll see a 4s1, 3d5, and I'll show you exactly how to do that. That's not copper, though. I'm not sure why they're calling that. That's manganese. So I'm not sure what they're getting at there. Okay, doesn't matter. Or chromium. I think that's chromium. This occurs because the 4s and 3d orbitals are very close in energy. These anomalies occur in the F block atoms as well, but we're not going to talk about that. And I think that's it. Good. Sorry, this is a very long one. I hope you could keep up.